Hi, chemistry students. Let's do another equilibrium problem, this time from a different angle, I would say. What we're going to do is, instead of being given the equilibrium constant, we're going to find out how an equilibrium constant can be determined from experimental data. So the problem would be something like this. We'd have some reaction, 2A plus B gives us 3C, all in the gas phase in this case, and we're given some initial conditions. In this particular case, we're told that there's 1.2 atmospheres of the chemical A, 0.5 atmospheres of B, and 0.55 atmospheres of C. Notice that everything's given as in atmospheres, so we're dealing with pressures, it seems. Later on, though, some spectroscopic means were used to find that the pressure of C was now 0.331. And so we're asked the question, what's the equilibrium constant for this reaction at the particular temperature it's being run? So the way to start off is to recall that we're being asked to find this case of P, and that P is very important. That little p means that we are studying something in terms of its partial pressures, not concentrations. It's your job to know that that p means pressures, all right? The equilibrium expression then has the same exact form that we've seen before. The C will be cubed because it has, the pressure of C will be cubed because it has a stoichiometric coefficient of 3. And similarly, if you look over there, the pressure of A is squared because the stoichiometric coefficient is 2. And that's exactly what we expect. So just once again, that's the equilibrium partial pressure of C in that numerator term, and the other terms are very similar then. So the first step, rewrite the reaction. Then we start making our ice table. All right, so we're all set. The next step in any one of these is going to be the same. We're going to fill in what we know. So the first thing we know is we were given the initial situation in terms of our partial pressures. All right, well, we know one other thing, because if you think about it, at this point in most of our problems, we would have probably calculated Q, which we could do here, but we don't have anything to compare it against. Q is useful when we can compare it to K. We don't know what K is, the equilibrium constant. So we do have this bit of information, that there is 0.331 atmospheres of C when the reaction finishes. So this is all the clues we have as to how to figure out what's going on in this reaction. Fortunately, we can determine the equilibrium, the direction the reaction is going to shift to get to equilibrium by just looking at one piece of information, and that is, how does C change during the reaction? The pressure of C, if we take a look at it, decreases from 0.55 to 0.331. Therefore, it's losing moles. That's the only reason its partial pressure would go down. So if its partial pressure decreases, that means it is being used up. So our chemical C is being used to make B and 2A's. So that means we're shifting left towards the reactants, and we can now complete the ice table. So we would be making our A and B, 2x, 1x, and we'd be using the C, minus 3x. That means we can now finish our equilibrium row by adding the column that it's in. So 1.2 plus 2x, 0.5 plus x, and 0.550 minus 3x. Fantastic. Well, now it seems like we may be finished completely except for one other clue, and that is we know the result of this algebraic equation. We know that this particular algebraic equation is equal to 0.331 atmospheres. We were told that. So we can rearrange that and find that, that x is equal to 0.073 atmospheres. Now that we know x, we can find the partial pressure of A and the partial pressure of B. And with those, we can plug them directly into our equilibrium expression in terms of partial pressures, plug those values in, and voila, do the calculation and find that our equilibrium constant is 0.035. There you have it. That's one use of equilibrium in the ice table, in this case finding the equilibrium constant.